9.2 magnitude. One single fault rupture that lasted at least 10 minutes straight. That's not a typo. 10 minutes of continuous violent slip along 1,600 kilometers of seafloor. On December 26, 2004, the Sumatra-Andaman earthquake didn't just flatten coastlines or generate one of history's deadliest tsunamis. It physically changed the planet, not metaphorically, not poetically, measurably. NASA scientists calculated afterward that the earthquake shifted Earth's rotational axis, shortened the length of every single day, and slightly compacted the entire globe. Drop a comment if you remember exactly where you were when the news first broke that morning. So here's the basic setup. The earthquake struck off the west coast of Aceh, northern Sumatra, at just before 8 in the morning local time. The India plate, dense and heavy, shoved underneath the Burma plate in a classic Megathrust rupture. That kind of earthquake doesn't just crack rock sideways. One plate dives down beneath the other, dragging massive amounts of crustal material downward toward Earth's core. That downward mass movement is the key detail. Everything that follows, the axis shift, the shorter day, the wobble, traces directly back to that single physical action of one plate subducting under another. Here's where it helps to think about a spinning figure skater. When a skater pulls their arms tight against their body, their rotation speeds up. That's not magic. That's conservation of angular momentum. The same physics applies to a planet. When mass moves closer to Earth's rotational axis, the planet spins faster. During the Sumatra Quake, an enormous slab of oceanic crust lurched downward and inward. Mass redistributed toward the center. Earth's rotation accelerated. NASA's Jet Propulsion Laboratory calculated the net result at roughly 3 microseconds shaved off the length of every day. 3 microseconds sounds trivial. It isn't. That's a real permanent instrument-confirmed change to planetary rotation caused by one event. And the axis shift is where it gets genuinely strange. Earth's figure axis, the axis around which the planet's mass is actually balanced, moved. Scientists measured the shift at approximately 2.5 centimeters, with some models suggesting the wobble reached as much as 25 millimeters in the direction of 145 degrees east longitude. That's not the geographic pole relocating in any dramatic way you'd notice walking around outside. But it's measurable, it's documented, and it happened because one catastrophic earthquake rearranged enough mass inside the planet to throw off the balance point. The Earth also became slightly less oblate afterward, meaning it flattened very marginally at the equator and compacted slightly overall. 1 part in 10 billion, but real. The measurement precision required to detect these changes was itself remarkable. Satellite laser ranging, bouncing beams off reflectors left on the moon by Apollo astronauts, confirmed the axis shift independently. Ground-based GPS networks worldwide recorded co-seismic displacement in detail, creating 3-dimensional maps of how the earthquake deformed the crust. These measurement tools didn't exist during previous megathrust ruptures in recorded history. The 1960 Great Chilean earthquake at 9.5 magnitude occurred before scientists possessed instruments capable of tracking planetary-scale rotational effects with such precision. The 2004 event became the first time humanity directly measured these planetary consequences from a single rupture. Now let's be straight about scale here. Changes in global wind patterns affect day length roughly 300 times more than this earthquake did. The natural Chandler wobble, Earth's ongoing rotational wobble, can swing up to 15 meters on its own. So the Sumatra Quake's effects, while real and measurable, weren't going to throw off your calendar or rearrange the stars. Tidal drag from the moon adds about 15 microseconds to the day every year, meaning the rotational change from this earthquake gets absorbed back into normal planetary drift relatively quickly on geological timescales. That context matters if you want to understand what actually happened versus what viral headlines claimed. The tsunami is the part most people remember, and for good reason. Waves reached 30 meters in height along parts of Aceh's coastline. The city of Banda Aceh, sitting closest to the epicenter, had roughly 20 minutes before the first wall of water arrived. More than 100,000 people in that city alone were killed almost instantly. Across 14 countries, the final death count reached approximately 227,898 people. The waves traveled outward at around 500 miles per hour through deep water, losing almost no energy over distance, which is why they reached Sri Lanka, India, Thailand, Somalia, and even showed measurable effects as far away as Mexico and Chile. In deep ocean water, tsunami waves barely register at the surface. They compress into low, fast-moving humps that ships barely notice. Then shallow coastal water slows them down and forces all that energy upward into walls of moving water that nobody outruns. The rupture itself set records that still stand. Longest fault rupture ever documented at somewhere between 1,200 1,300 kilometers of continuous slip. Longest duration of faulting ever observed, running for at least 10 full minutes. The energy released equaled more than 23,000 Hiroshima-type atomic bombs. In the full century between 1906 and 2005, roughly 1/8 of all seismic moment released by every earthquake on Earth combined came from this single event. Seismometers worldwide picked up the vibrations for days. Compressional waves reached the opposite side of the planet in about 22 minutes. Vertical ground movement of 3 millimeters was recorded in Oklahoma. The entire planet vibrated by up to 10 millimeters. Scientists describe it as ringing Earth like a bell, and that analogy is actually mechanically accurate. The coastlines themselves were permanently redrawn in some areas. Uplift forced coral reefs above the water surface along certain stretches. In other locations, subsidence pulled shorelines below sea level permanently. The geography of parts of the Indian Ocean basin is measurably different today than it was on December 25, 2004. That's a scale of geological change that normally takes centuries of gradual tectonic movement to accumulate. Here, it happened in 10 minutes. The disaster also exposed a critical gap in global warning infrastructure. The Indian Ocean had no coordinated tsunami warning system in place at the time. Better monitoring networks and public education about tsunami behavior would likely have saved tens of thousands of lives in the hours the waves took to reach more distant coastlines like Sri Lanka and India. Active region 4,478 notwithstanding, the 2004 Sumatra earthquake remains the cleanest demonstration the modern era has produced of how a single rupture can scale from local catastrophe to global geophysical event. The science behind the axis shift isn't exotic. It's the same rotational mechanics governing every spinning object in physics. Mass moved inward. The planet sped up. The balance point shifted. What makes it remarkable isn't the physics. It's the sheer amount of mass involved, moving fast enough, deep enough, to make those effects measurable at a planetary scale. Scientists are still analyzing long-term geophysical data from that event more than 2 decades